Hello there, students and friends. This is now the answer and solution to question number 5 involving cross product of two vectors. So stick around, watch and learn. The question reads, vector A has a magnitude 12 units and is in the direction of the positive x-axis. So in the diagram, we have here vector A. It is directed towards the positive x-axis. Its magnitude is 12 units, while vector B has magnitude of 8 units and it lies in the xy plane, making an angle of 30 degrees from the positive x-axis. Alright, so as shown also here, we have here vector B. Its direction is defined by the angle phi, alright, which is 30 degrees, alright, from the positive x-axis. Notice also that the two vectors are connected tail to tail. So the question, find the vector product represented by vector C. The vector product of vectors A and B, right? Or A cross B. The product of A and B can also be read as the cross product A and B. So, what is our formula to determine this vector product or cross product? Alright, the formula is C is equal to AB sine of the angle phi. Alright? You may notice that uh, the quantities A, C, and B are in bold capital letters. Right? That is how uh, we represent vector quantities. So in this formula, the letter capital C is not in bold letter because capital C is just the magnitude of the vector product of vector B and vector A, right? It's just the magnitude. AB are the magnitudes of the vectors A and B, and the Greek letter phi represents the angle between vectors A and vector B when placed tail to tail as shown in the diagram. The vector product vector A cross vector B of two vectors is a third vector that is perpendicular to both vector A and vector B, which can be obtained either from the magnitudes of the two vectors, the angle between them, and the right-hand rule, or from the components of the two vectors. Alright, so the first method that we're going to use is what is mentioned here, basing the solution from the magnitudes of the two vectors, right, given the angle between them, and using what we call a right-hand rule. Right? So what is this right-hand rule? Right. Before that, uh, let us emphasize that the two vectors, vector A and vector B, actually lie in the same plane, the xy plane. Or we can say that vector A and vector B are coplanar, right? So, the vector product or the cross product of vectors A and B, all right, is represented here by vector C, right? And this vector C is in fact directed towards the positive Z axis, right? How is this vector product, how is the direction of the vector product determined using the right hand rule? All right, so we have here the steps that you have to take in order to determine the direction of the vector product of two vectors such as vector A and vector B. First, you have to place uh, the two vectors, all right, vector A and vector B, tail to tail. That is already what is shown in the diagram, all right? So their tails are located at the origin of our x, y, and z coordinates. Sometimes we call it the tail-to-tail method of vector diagram. Next, you have to point your fingers of your right hand along vector A, right? So, these four fingers will represent the first vector, vector A, while the palm of your right hand, all right, it will be facing, the right palm will be facing the second vector, which is vector B, right? Then, number 3, you have to curl your fingers, the four fingers, that is, curl the four fingers towards vector B, right? And the fourth step is for you to determine and describe the direction of the vector product A cross B. That is represented by the thumb, which points in the direction of the vector product or cross product of A times B. So in the accompanying diagram here, okay, that direction of your thumb is what is represented by the vector product, all right, A cross B. So the direction, the four fingers, before they are curled, the four fingers will actually represent the first vector, in this case, vector A, right? While your right hand palm will be representing the second vector, in this case, vector B. And then as soon as you curl your four fingers, all right, towards your palm, your thumb, therefore, will be pointing towards the vector product or the cross product. That is how we are able to determine in this original figure that the vector product represented by vector C is indeed directed towards the positive Z axis. For our first method, we simply use the formula magnitude of vector C is equal to magnitudes of vectors A and B sine of the angle phi. Alright? So the magnitude of vector A is 12 units, while the magnitude of vector B is 8 units. So 12 times 8, then multiply it by the sine of the angle phi, which is 30 degrees. Doing our math, what we get is the vector product. Alright? Vector product C, which is equal to 48 units, and the unit vector K suggests that the vector product C is directed towards the positive Z axis. That is the first method. Okay, so it's just very simple. Now, so that we can check this answer, we will also show another method, and this is using the component method. We first identify, the x, y, and z components of the magnitude of vector A. That is, ax is equal to 12 units, and it has no y component and no z component. So ay is 0, az is 0. For vector B, the magnitude of the x component for vector B is 8 cosine of the angle phi 30 degrees. Cosine 30 degrees is 0.866 multiplied by 8, we get 7 units. The y component is equal to 8 multiplied by the sine of the angle 30 degrees, which is 0.5 times 8. That gives us 4 units. It has no z component, so that means bz is equal to 0. So we now proceed in getting the vector product. We label it as vector C in bold letter. Alright? So the formula in terms of the components, we first determine the magnitude of the x component of vector C. And this is equal to the product, the product of the y component of vector A and the z component of vector B minus, the z component of vector A multiplied by the y component of vector B. Substituting, we get ay is 0, bz is 0, az is 0, but by is 4. So it's obvious that the magnitude of the x component of vector C is equal to 0. Now, for the y component of vector C, the magnitude is equal to az times bx minus ax times bz. Substituting, az is 0, bx is 7, minus ax is 12, and bz is 0. So again, obviously, the magnitude of the y component of vector C is equal to 0 as well. For the z component of vector C, the magnitude is equal to ax by minus ay bx. Substituting, ax is 12 units, by is 4. So 12 times 4, that is 48, minus 0, which is ay, multiplied to 7, which is bx. 0 times 7, of course, is 0. So the magnitude of z component of vector c is equal to 48. And we say that the vector product, okay, vector product c, which is the cross product of vectors a and b, is equal to 48 units, right? Directed in terms of the unit vector k, so 48k, which suggests again that the vector product that we are asked to find has a magnitude of 48 units, both directed towards the positive z-axis. This is now question number 2. Given two vectors, vector A equals 4.00 I plus 7.00 j, and vector B equals 5.00 I minus 2.00 j. Right. So, just a refresher, this way of expressing the vector means that vector A has an x component, okay, whose magnitude is 4 units, and it's directed towards the positive x-axis, while its y component has a magnitude of 7.00 units and is directed towards the positive y-axis, while vector B, its x component has a magnitude of 5.00 unit directed into the positive x-axis, while its y component with a magnitude of 2.00 unit is directed towards the negative y-axis. Okay, letter A question. Find the magnitude of each vector. Question letter B. Find the vector product A cross B. And letter C. What is the magnitude of the vector product? So, our solution for letter A, finding the magnitude of each vector, the formula to determine the magnitude of a vector, for example, magnitude of vector A, it's just equal to the square root of the sum of the squares of vector, of the x component and the y components. That is square root of 4.00, then square it plus the square of the y component, 7.00, right? Doing your math, we will get as the magnitude of vector A, 8.06 units. Similarly, for vector B, the same formula applies. Square root of 5.00, then square it plus the square of the y component, negative 2.00, right? So again, simplifying, you will get as the magnitude of vector B, 5.39 units. All right, then let's proceed answering letter B. We are asked to find the angle phi, all right, between the two vectors, vector A and vector B. Now, in doing this, we assume that in your diagram, you have to draw the two vectors in such a way that they are connected tail to tail, right? And then, uh, one particular method of determining the angle between two vectors that are drawn tail to tail is to use the scalar product or the dot product of the two vectors, right? We recall that the formula for determining the angle, in this case angle phi, is just equal to the arc cosine of the dot product of vectors a and b divided by the product of their magnitudes. So in a short while, we will see how we will be able to calculate for the angle phi. Alright, so moving on with our solution in finding the angle phi, alright, between the two vectors. We already have here the vector diagram, alright. As described earlier, a vector A, which is represented here by the red vector arrow, alright, and vector B represented by the blue arrow. They're connected tail to tail, right? So using this formula, we're going to determine that angle phi, right? It is the angle between the two vectors, labeled here as the Greek letter phi. So we first determine the numerator in this formula, and that is the scalar product a dot b. That is equal to the x component of a multiplied by the x component of b plus the y component of a multiplied by the y component of b, right? Substituting, we have for ax it's 4.00, for bx it's 5.00 units, plus 7.00, that is the value of ay multiplied by negative 2.00, which is the value of by. And doing your math, we will get, all right, as the scalar product a dot b equal to 6.0 units. We then proceed in determining, all right, the denominator in this formula. That is the product of the magnitudes of the two vectors a and b, right? So these two values were obtained earlier on. Okay, you can check on that. The magnitude of vector A is equal to 8.1 units, while the magnitude of vector B is equal to 5.4 units. So when they're multiplied, we get the product of the magnitudes of vector A and B equal to 44 units. Now we are ready to calculate for the angle phi. Alright, we just substitute the dot product a dot b is equal to 6.0, alright, divided by the product of the magnitudes of the two vectors, which is 44. Using your scientific calculator, you will get that the angle phi is equal to 82 degrees. Alright, so that 82 degrees is the angle, alright, formed between the two vectors. In finding the vector product A cross B, labeled here as vector C, we use two methods. The first method is what we call the component method. One thing nice about the component method, we actually don't need to know the angle between the two vectors, right? So, how do we do the component method? We first specify each of the magnitude of the x, the y, and the z component of each vector. For example, vector A its x component is equal to 4.00 units. Its y component is 7.00, and it has no z component. Az is equal to 0. While the x component of vector b, we have 5.00. Its y component, by, is negative 2.00 unit, and it has no z component either. Then we proceed in finding the x component of the cross product labeled vector c, right? Using this formula, right? So the x component of vector c is equal to the product of the y component of vector a and the z component of vector b minus the z component of vector a times the y component of vector b. Substituting, we get 7.00 multiplied by 0 because z or bz is equal to 0, right? Likewise, az is also equal to 0, so that even if by is or has a value equal to negative 2.00, right? Multiply it by 0, of course, the magnitude of cx will still be equal to 0. Now, for the y component of vector c, we have the formula. Cy is equal to az multiplied by bx minus ax times bz. Substituting, az is equal to 0 multiplied by bx, which is 5.00, minus 4.00, which is the value of ax, and bz again is 0. So, simplifying, you will still get cy equals 0. Moving on to finding the magnitude of c along the z-axis, or the z component, we have the formula ax by minus ay bx. Substituting, 4.00 times negative 2.00, that's the magnitude of by, right, minus ay, which is 7.00, and multiplied by bx, which is 5.00. Simplifying, we get as the component of cz equals negative 43.0 unit. So we conclude that the vector product A cross B, labeled here as vector C, is equal to negative 43.0, okay, and it is also represented here by the unit vector k, meaning this vector product is indeed directed along the z-axis, but look, it has a negative sign, which means that the product of vector, or the vector product A cross B, okay, represented by vector C, is indeed directed towards the negative z-axis. So that's how we got it using the component method. To check, we now make use of the calculated angle phi, and using the formula, right? The formula for determining the component, the magnitude of vector product labeled or represented by capital C is equal to the product of the magnitudes of vectors A and B times the value of sine of the angle phi. All right? So this is the formula that we're going to use since we already know the angle phi. So we simply substitute. We have, for the calculated magnitude of vector A we got earlier, it's 8.06. Multiply that by the computed value of the magnitude of vector B, also shown earlier, 5.39, and then multiply the product by the value of sine of the angle 82 degrees using your scientific calculator. Okay, we will get as the magnitude of vector C, that is equal to 43.0 units. Now, how is the direction of this vector product determined? All right, if this is the method you use, okay, using the formula, and you haven't done the component method yet, how will you be able to determine the direction of this vector product? Of course, you use the right-hand rule. If you recall, the right-hand rule says that you're going to make sure that the two vectors, okay, when you have it drawn like this, they must be connected tail to tail, right? And the four fingers of your right hand represent the direction of vector A, while your palm, okay, the palm of your right hand represents vector B, right? So, if you're going to curl the four fingers towards your palm, try to observe where the thumb of your right hand is pointing, because that thumb is pointing towards the cross product of vectors A and B, right? You should find that the direction of your right hand thumb is towards, all right, or perpendicular to the screen or to the page. In short, it is directed towards the negative z axis, which confirms our first answer when we did the component method, right? So our answer using the component method tells us that the magnitude of the vector product is 43.0 units, and its direction is towards the negative z-axis. So using the formula and applying the right hand rule, we also have the same result. It has a magnitude, cross product labeled capital C, has a magnitude of 43.0 units, and using your right hand rule, we see that its direction is towards the negative z axis. So that's it. We are done with our computation and interpretation of our answers to question number 2. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.